that are good students, they'll put the time in doing the homework in a timely way when I ask them to. They'll do the homework, they'll look and see if the answer's right. If they don't understand something, they'll see me, send me an email, get on GroupMe or whatever you're gonna use. Are you gonna use GroupMe or what you're gonna use?
I'm not sure yet. GroupMe.
GroupMe is I tell you the truth, that is an incredible tool because the students interact, and I don't care what you say about me, by the way. It doesn't, you can't bother me on there. You can say anything you want. You're a horrible instructor, and how can you possibly say that? And they say all stuff, that doesn't bother me at all. As a matter of fact, it's better you feel free to say things the way you would normally. And I don't generally poke my nose in there unless somebody like pings me that there's an issue that nobody understands, then I will. But please think about, well, I should say, schedule your time in a way that you can block out 2 or 3 hours between classes, every class period, to do the homework. Make sure you get the homework done. Some people do it real quick, right? There's some people in here that fly through all this stuff. Some will struggle. It's just the nature of this course. This is the first really difficult course you've had, in my opinion. Now, I know you've had physics and you've had calculus, and you probably had circuits, right? Mm-hmm. All right, Dave Irwin's circuits classes, did you all have Irwin? He's a great teacher. That is still very low-level mathematics, in my opinion. This is going to get a lot tougher, and it requires a lot more focus, almost creative imaginations, and the ability to do really deductive thinking at a higher level. Now that's what I'm saying because I've taught this many times, and I know people say, I've never seen anything like this. It's just driving me nuts. And it's engineering. That's the reason you're paid so darn much, is because you're going to be doing work that very few people can do well. It's a very challenging course. I'm telling you this, I don't care what you've heard. I've done this too many times, and I know it. Now, the way I lecture normally is I have my topical notes and stuff like this. This is sort of what I call it, it's sort of my major themes that I'm going to talk about. If you've got questions about other things, we'll talk, related to this material, or questions about the homework, I'll jump right in on them. Usually at the beginning of every lecture, I start by asking, are there any questions about the homework? Now, usually 1 or 2 people will have questions, but the ones that I like is when everybody is a little baffled or confused by something. I like getting those out of the way first, and usually somebody sends me an email, or they'll say, look on GroupMe this, and now I'll address that. Now you get some people that just, they even do the homework, they ask you to do all the homework for you. I'm not gonna do that. I will do the ones that I think are of importance that a lot of people are having trouble with. So with that in mind, unless there's any other, are there any questions at all? I don't take attendance. I'm not Gross. If you've ever had Gross, he takes attendance. And if you're not there, you lose a point or something like this. What I normally do is I ask people to be here. You don't have to be here if you don't want to. But on every Friday, if you're not here, then you get a 0 for that quiz, unless you have a university-approved excuse, all right? There are going to be about, I'm going to say 10 to 12, maybe 15, maybe 13 quizzes, something like that. I drop the lowest quiz grade and I average them. Now they're all out of 10 points on these quizzes. My tests are out of 40. I usually have 4 major questions with multiple parts. And I can tell you that, what is this class about? It's under 30, it's about 25 students approximately. A class like this, you're probably going to see a lot of interaction online if what I think is going to happen. So there'll be people that are asking questions, answering questions, and I encourage you to do that. And if you can set a time when most of you are online at night doing homework, it is even more helpful, because that way all the classes sort of, they're looking at the same time and they have the same level of concern about something. Remember, every Friday quizzes, and they're usually at the end of class, but sometimes I give them at the beginning, all right? All right, that's fair. So now, I guess the last thing I have to say, unless they changed the book and didn't send me an email, this is the book. Do you all have, anybody have this? Does anybody have this book? Does anybody have the book? Has anybody gotten a book in here? Well, you don't surprise me, because this is the way I'm noticing. It used to be that students would order this stuff from India and places like that where you get them real cheap, and they would get knockoff copies and stuff like this. I think I'm not sure of this, I think they have Chinese versions of this, by the way. I think they do. I say that tentatively. I know they have Indian versions of just about any book I teach. But you need the book, all right? You don't get to use the book on a test. I say you need it. I'm not sure you absolutely have to have them. You have to have access to the problems. That's what I should say. All right? So you need access to the problems. I will give you the solutions to the problems. I may even give you the problems. I'm not sure yet. I don't think I can get too much trouble for the copyrights, but I would advise you to buy the book. And one other thing I'm going to say about this. Now, in my life, I kept every one of my engineering books and my math books and my physics books. These are things I write in. I encourage you to bring them to class and write in them. You know, if I tell you something this is a trick, here's how you do it, write it in here. You won't lose this. Not usually, at least. It's too much money. You'll lose your notes. All right? You'll lose all sorts of things, but you won't lose this. And I still have my books, and they're still annotated the way I did it. And that's what I go to if I have a question, 90% of the time. Nowadays, I think you just get on Google. But most of the time, if you're looking for specific tricks, stuff like this, and you know you saw it before, it's probably in one of your books. And that's right. I encourage you to buy it and keep it. So that's the book, and I'll have that for you too. I think the bookstore probably has it. Has anybody looked at the bookstores to see if they have this book? No, all right. Can you do this for me next time? Please make sure at least you can buy the book, they have it, so I don't have to order any more copies. Because if you're lacking in it, if the bookstores don't have them, I have to tell somebody to order them. And that's what I'm going to ask you to do, all right? Now, so this is signals and systems. I'm just going to start right in. So what are we talking about? Well, in circuits, you basically talked about two forms of a signal. I'm going to stick with voltage for now. You had a voltage or a current. You could talk about power being the product of voltage times current, but you were talking about terms that are electrical terms. You're not talking about a signal in some abstract sense without meaning. Now, voltages is like electric pressure. You know that, right? When we talk about any of these signals, I mean, you had a very, very fundamental look at that. You basically had either DC, it means it's time invariant voltage, like a battery, or you had something that was at a constant frequency that was sinusoidal or cosinusoidal, right? And then you went into the phasor domain. Or you had things that are called transients, but there were only RC or RL decays, where it's exponential decays. Those are the three forms of signals you were exposed to. Isn't that right, class? Mm-hmm. All right, here you're going to get everything. You're going to get chaotic signals that have everything in the future is not based on the past, they're uncorrelated. You're going to get signals of every type that are based on what you're going to be exposed to in the real world. And the analysis tools that we have are primarily going to be done in what's called the frequency domain, not the time domain. You got a little exposure to that. Remember when you did phasor domain problems? What did you do? Well, you said, I'm going to get rid of frequency. You took e to the j omega t and said that was equal to, and let me put this down here so I can just draw you into this lecture in an understanding way. Normally you said that you had e to the j, and now I'm going to put down just theta. Theta was usually omega t, all right? And you said that was cosine of theta plus j sine of theta, right? Does anybody remember what law that is, or what rule? What term used to describe this? Eulers, right? Eulers, E-U, right? L-E-R-S, Eulers. This is one of Eulers' identities. You have to know this. The other two you should know, actually you have to know these two, is cosine of theta is equal to e to the j theta plus e to the minus j theta over 2, and sine of theta is equal to e to the j theta minus e to the minus j theta over 2. Now those are things you're exposed to in terms of definitions, but the real thing you had was when you had a phasor term, say you had V as a phasor and it might be some magnitude A at an angle theta. That was called a polar way of representing it. A could be like 10, theta is 30 degrees. Y'all remember those, right? Mm-hmm. That could be also written as A times e to the j theta. That is the exponential way of rendering that, right? And then you could say one other thing. This is in the phasor domain. The relationship between phasor and time domain was something that V of t, that would be in the time domain, was equal to the real part of, and here you had V phasor times e to the j omega t. That's the relationship from time going back, from frequency to time. Do you all remember this, class? Mm-hmm. Simple example just to bring you up to speed. And this is at a constant frequency. All your analysis was done at a constant frequency. You all remember that, right? Usually it was 60 hertz, which is really 120 pi radians per second. But getting back to this, a simple example, if I said I had a circuit like this, and I had a voltage, and say it was 10 times cosine of 377t plus 20 degrees, so that's my voltage. And then I had a resistor here, R, and say I had an inductor here, L. By the way, this is a question you get sometimes, a question just like this when you go for an interview and they want to make sure you understand the basics. They do this nowadays. They don't trust colleges. And they want to know what I of t was, all right? They're just wondering, how would you solve that problem? Well, if you're a physics major, a mathematician, you write a differential equation, right? You know that you could write a differential equation, and the voltage here is simply I of t times R, right? And the voltage here would be equal to L times di dt. And you would say, well, the sum of the voltages around that closed loop would be equal to 0, right? And that would be a differential equation, and you would solve the differential equation. You all remember doing that kind of crap? Mm-hmm. Right, back in the day when you were over in the math department, right? But as engineers, we don't do that, do we? Mm-hmm. If that's a constant frequency, that's all you need to know. Mm-hmm. Now you go to the phasor domain, and you're going to say that now, what I have is a voltage here, and I just need the magnitude, 10, and I know it's at an angle of 20 degrees, right? Now, in the phasor domain, resistors are just resistors, right? So it's just R. Right? In other words, the impedance in the phasor domain is the same. I could put R as 10 there or 20, but I'm going to leave it as R. And I also know one other thing, that the actual voltage across an inductor, if you think about the phasor impedance of that is J omega L, right? J omega L is this impedance, right? So now if I want this current, and it would be a phasor current, that would be this voltage, which would be 10 at an angle of 20 degrees, and it would be divided by R plus J omega L, right? Now you need, if that was L given, you would need to know omega to get omega L, which is an impedance. Do y'all remember doing this, guys? Everybody? All right, now that's going to be a number. It's going to be a magnitude, and I'm just going to call it some I naught, a magnitude, and it's going to have an angle. So it's going to be at some, and I'll call it theta I. Now that is a complex number, and it represents a magnitude and an angle. If I wanted the time domain is the observable domain. This is not observable. In a sense, you could measure it if you had the right equipment, but it's not in the real world. It's a fake domain, you might say, all right? The thing we could observe if we had a current meter, real-time current meter, would be this. It would be I of t would be equal to the real part. Remember, this is the same thing as I naught e to the j theta I also, right? It would be the real part of, and here it would be this, so it's I naught e to the j theta I. That's this. This is voltage, this is current over there, so, but it's equivalent to the phasor term here. And now I multiply it by e to the j omega t. And that would be I of t. I'm going to complete this because some people sometimes don't remember this exactly. Now remember, the real part means the non-imaginary part, if you will. So I look at this, and I say that's the same thing as taking the real part. Well, I know I can, if I have e to the a times e to the b, it's the same thing as e to the a plus b. Do you all agree with me there? Everybody? So what I can do is write this as some I naught e to the j, and here I can put theta I plus omega t. Most of you have seen something like this. I don't know how Dave Irwin did it. He probably did a lot better than me. He's the best circuits teacher on the planet, in my opinion. And he's very clear and precise when it comes to important things. But you may not remember these details because you didn't have to keep going back to them. You were just exposed to them one time. Now when I take a look at the real part of that, right? It's the real part of I naught, and now I would use Euler's identity right here. This is Euler's, right? And I'd go ahead and I'd say it's I naught times the quantity cosine of omega t plus the phase angle of I plus j times the sine of omega t plus the phase angle of I. And this is the thing, a lot of people don't quite get it, and they won't ask me what real means and what imaginary means. When they say real, the cosine has no j in front of it. That's the real part, got me? The j means it's imaginary. When you put re, it means you only want to retain the real component of that. So that means this, and I'll put it up here so you can see, would just be equal to I naught times cosine of omega t plus the angle associated with the current. And that would be observable. That's in the time domain. So I'm bringing that around to show you at least you've been exposed to analysis at a constant frequency. Not at a variety of frequencies like we're going to do, but a constant frequency. And everybody remembers this, right? Mm-hmm. So now let me go ahead and start. Once we did that. So what we need to do is define carefully how we can talk about voltages or currents in terms of the building block functions and describe all, you might say, all the most common voltages and currents so we can get on with our analysis. So that's the first thing I'm going to do. Also going to make mention of one thing. In today's, and matter of fact, almost everything, I can think of one thing that's analog, but almost everything is digital, right? When you say, well, what does digital mean? Well, it's binary ultimately. It means it's only two states. It's either a 1 or a 0 per se. But really what digital does also, it means everything is got discrete points in time, if you're talking about a time domain function, that it's sampled at or it's measured at. It's not at a continuous time. All right, when you think of long playing records, do you all remember these things? All right, when you put the needle on there, it would generate a voltage in the actual, when you put it on a phonograph, the needle would actually vibrate and induce a voltage, either through a transformer or through a ceramic cartridge, and there would be a voltage induced on it. That voltage, if you would track it, is continuous. There's no variation. Follow me? I mean, there's no break. It's continuous. All right? It's got a finite amplitude, and it exists for all time. In the digital world, really the discrete domain, we sample that thing at a very high rate, and we only retain the value of the voltage at the samples. And we also introduce another form of error, and that's called quantization. We don't allow the voltage to have all values, but there's going to be maybe 512, maybe 1024 values. All these values are going to be 2 to some power n. Now that's something you have to keep in mind. So we'll start in the analog domain, but we'll go to the digital because that's really where everything, or I call it the discrete domain, where everything is done. Was our next game basketball game on Saturday? Or is there one before? Is there one tonight? Who are we playing? We're playing Vanderbilt tonight. You should know that. I got tickets for the one on Saturday now. Didn't know that. All right. So now, you don't have to write this, just listen, because this is just basics. If we talk about an analog signal, and this is time, and say this is V of t, it could look like this. All right? That's a simple strip chart. That's how it used to be shown when I was sitting where you are. We had tons of strip chart data taken from satellites measuring the voltage potentials on them and stuff like this. There's just tons of strip chart data that you could look at, and there was also a reel-to-reel tape that you could access. But that was normal. Nowadays, you don't get that. What you get is something where at discrete points in time, you're going to sample that signal, spaced a continuous point, or they're spaced at a delta t that is the same. And what you're going to do is have this. Down here, you're going to simply see this. And I'm putting this is called a stem plot. On MATLAB, you'll see this kind of stuff. Basically, you're going to see this. And instead of t down here, they'll have n. And n usually starts at 0, by the way. Not always, usually it's 0. That's the stuff you're going to see. Now, I didn't show quantized values here, that comes later. But now we're going to have discrete data. This is continuous time, this is discrete time. There's no big mystery here, right? We'll talk about this in a bit. So for continuous time data, now we have to talk about really, I'll get the energy and power in a second, how we're going to describe functions in continuous time besides just cosines and sines or exponentials. And we want to do this in a way that will allow you to describe any function I draw fairly easily. So we start with these things that are tools. And the first thing you talk about is these are going to be functions. It's called the impulse function. The symbol for it is delta t. Has anybody seen this? Or Dirac delta? Do you remember that at all from math? Did you have it in your calculus courses and stuff, or where'd you get it? Anybody? Remember? How many have had it? I see one head bob. That's it? All right. I don't know if you have or not. Sometimes they cover it in your differential equations courses. Sometimes they don't. But anyway, what is it? Well, if this is time, here's what this is. It's a function that looks like this, where the width is 1 over t, or I'm sorry, 1 over epsilon. And the height, this is one way to describe it, is simply going to, the width, let me do it this way, is epsilon, and the height is 1 over epsilon. Now, when you look at that right there, it's really the limit, delta t here, is the limit as epsilon approaches 0 of this function. Now, I could mathematically write it, but it's easier to see it graphically. Well, as epsilon's going to 0, where's this guy going to, the value here? Infinity, right? But what's the width going to? 0. It looks like a needle, right? So the way they actually show a delta function is this. That's the symbol. It's just delta t. It's a spike. Right? The one thing about this, it has an area that's a constant, 1. Do you notice? If you take a look at the height times the width, it's 1. Follow me? Mm-hmm. But what this is doing is tending to a spike, and that's important. Now, when does it go to that spike? It's when the argument in here is 0. Follow me? So let me just go through this with you, because you haven't seen delta functions yet. So if I put this, I'm going to show you one other thing about a delta function. If I did this and I put delta of t minus 5, and I wanted you to graph that on this plot, where this is going to be the function, this is my f of t. Well, where would it be? When does this function go to 0? When does the argument here go to 0, class? T equals 5, right? So you spot 5 here, and you simply do this. And the height would be infinite, but this is, the way they do it, always put a little arrow there. That means a delta function. Got me on that one, class? Just hang with me. Now, what if I did this? That's this function. Now, suppose I did call it g of t, and I'm going to let g of t be equal to delta of 6 minus t. Now, where's that function? Remember what I told you. The argument in there has to be 0. When is t minus 6 equal to, I'm sorry, 6 minus t equal to 0? T equals
6.
It would be at t equals 6, right? Out here. What if I did this? Minus 6 minus t equals 0. It would be t plus 6 equals 0, or at minus 6. Follow me? Mm-hmm. It would be down here. That's my point about delta functions. All right? That's it. Now here's another thing about delta functions that are important. And by the way, we can approximate delta functions with voltage generators. So this is something that actually we can make something approximately like a delta function, and we can put it as the input of circuits and get all sorts of interesting information. Not just circuits, all sorts of systems. So keep that in mind. This is something that's actually, we can approximate it for analysis. Now, here's the thing about a delta function that's so interesting. If I take any function, well, let me do it this way. If I take any function and I integrate that function from minus infinity to infinity, and I'm going to say I have a function g of t, and I multiply it times a delta function, times delta of, say, t minus 5 bt. This is important. This is called a sifting property of the delta function. It's why they're so valuable. Now, when I look at that, I know that delta function is 0 everywhere but at t equals 5, correct? Y'all agree with that? Mm-hmm. As a matter of fact, I could make the statement that this right here could be rendered as simply, since it only exists when t is equal to 5, I could take that g out in front and put g of 5, right? Times the integral from minus infinity to infinity of delta of t minus 5 dt. You all agree with me? The reason I can do that, this is 0 everywhere but at t equal 5. So really what I just need is the value of g of 5, right? And I know this integral is going to be what? What is the integral of a delta function from minus infinity to infinity? By definition, it is 1, right? The area is 1. So that means I really get just g of 5. And why is that important? Because it sifted the value of that function at 5. As a matter of fact, I don't have to put the number 5 down. What I can do is say just t minus tau. This is going to be important in a bit. And now it would be g of tau. And this, make that tau, would be simply g of tau here. This will come in handy when we talk about something called convolution. So whenever you have delta functions, they're beautiful things to have if you're doing integration, because you really don't do the integral. You just look at where the thing turns on, evaluate anything next to the delta function, where it turns on, pull it out in front of the integral, and multiply by 1. You got me on that, class? Now there's some more tricks to this, but this is exposure. You have to know why this function is important. You may not see why this sifting property will be useful, but you will. All right, now, having said that, that's our first function that you haven't seen. It's a building block function, delta. Now we do something, and this is just common, to build the rest of the functional arsenal, at least most of it. What we do is we integrate these functions. So the next function we talk about is something called the u of t. I call it the switching function. U of t, write this down please, you don't know this. U of t is really something, it's going to be a 1 or a 0. That's it. U of t is really the integral from minus infinity to t of delta tau d tau. Now let me explain that. You know the area under a delta function is 1, correct? Isn't that right? Once you integrate through the delta function in time or any domain, you got 1. So this delta of t right here, when I look at the u of t being defined as the integral of delta of, I'm using a dummy variable, tau d tau, from minus infinity to t, what I really mean is this. If you think about it, and I'm putting just tau in here. If I have a delta function here, and this is delta of tau, right? Versus tau. Well, if my t is back here, say I'm going to integrate my t's below 0. Well, it never hits the delta function, it's just 0, correct? Mm-hmm. But as soon as it goes through the delta function, it's 1. So this functional form is 0 for really t less than 0, and it's equal to 1 for t greater than 0. This is called the u of t function. And it's used all the time. You're going to see this. How many have seen this before? Have you? In what course? Remember? What? In DiffyQ? Okay, that makes sense. I'm surprised you didn't see the delta, because usually you cover the delta function, then the u of t, as ways of, as something that's useful to solve differential equations, usually with Laplace transforms, by the way. So what does this look like, this u of t? Well, graphically, it's this. If I put it in the time domain, it's this. And this is u of t. It's just this. It looks 0, then it goes to 1. And it stays there forever. Got me? Now, when does it do that transition? It's when the argument of the u of t is 0, just like the impulse function, right? When whatever's in there is 0. Do y'all follow me on that? Now, I'm going to keep going on this one. And make sure you see this. So what would this functional form look like that I'm going to put up here? Suppose I want to know what, and this is at 0, I want to know what u of t minus 9 looks like. Well, what does that look like if you were asked to sketch it? What do you always look for in these things? Where the argument does what? Goes to 0. When does t minus 9 go to 0?
When t equals 9.
T equals 9. So you find 9 right here. And you just say it's 0, 0, 0, 0. At 9, it goes up, stays at a value of 1. That's it. All right. What about if I had t plus 9? What would that do?
It's
Anybody?
9, negative 9, so it.
Now it does this. This would be minus 9. Boom. Stays at 1, right? I'm not done yet. I want to make sure I expose you to some other thoughts. Everybody follow me? It's that easy. How about this one? Suppose I put, this is versus t, here's my origin. I want u of minus t. What does that look like? You're going to get a lot of this. It's forced you to think outside the box, you might say. You don't see functions like this in your math courses. They don't start putting negative signs in there and stuff. Well, what does that look like? What's the argument? It transitions when this is 0, right? But anytime it's greater than 0, it's 1, correct, class? All right, now, minus t is 0 happens at 0, right? So this is the transitional point. Now take it a little bit less. What about t minus 1? Well, if I have minus 1 times a minus sign, that's plus 1, right? It's on. This does this. You basically took the u of t and just flipped it on its axis. All right, that's all you did. Got me on that one, everybody? All right, now what does this look like? Think about what I'm saying. U of minus t plus 5. What does that look like? First, where does it transition? Minus t plus 5 is 0, or t equals 5. Do you agree with me? Mm-hmm. So that's where things happen. Right? Minus 5 plus 5 is 0. Now, take it a little less than that. Say t is 0. Well, that would be u of 5, right? What is u of 5? 1, right? So it looks like this. Now, when I call this, basically, if I made this a more general statement about this, I would say, in general, if I had u of t minus tau, or better yet, tau minus t, do it that way. Tau minus t, what that is this. It's basically something that's like a curtain. And this would be tau. And as tau would be at 0, would be here, it would be on all the time, goes off at 0, right? If tau is minus something, then the curtain moves this way. If t is plus something, it moves this way. Do y'all see that? Mm-hmm. It's like drawing a curtain. Think about that, because you're going to see this a lot with some of the analysis we do. Do y'all see that, class? Now that's u of t. That's the second function. And remember, the argument's essential. Where it goes to 0 is the place there's a transition. And then you got to find out of a little bit before that it was either on or off. And then you know the other side's the opposite. All right. That's u of t. The next function, anyone want to take a guess what the next function is if you think about the progression of things? The delta t was the u of t was related by the delta t by integration, right? Mm-hmm. What do you think might happen again? We integrate u of t. Now we get something called a ramp function, r of t. R of t is simply equal to the integral, right here, from wherever this is it, all right? It's going to be, say, from minus infinity to t of u of tau d tau. Now this is the ramp function. So what is this really? Well, u of t is either on or it's not, right? If I just have t as the argument here, right? Well, this thing always starts at 0, doesn't it? Right? I mean, if this is the function, it's 0, less than 0, so we don't need to integrate 0, right? Mm-hmm. So we start at 0 and we go to t and we integrate this. So that means it's always a 1, right? And that means the integral of this is just t for t greater than 0, and it's 0 for t less than 0. This is called a ramp function. Now you'll notice that for t less than 0, it's not negative t. Do you all follow me? A straight line equation where like f of t is t would have negative and positive values. Do you all see this? This is something that only exists for t greater, or really the argument greater than 0. And this is the r of t. Slope on this is 1. This is R of t. And it really is just t u of t. Got me on that, class? It's just related to the integration. So far, there's nothing here that really is threatening you yet. Maybe the delta function made you a little uneasy, but that's all it is this is t. All right, now, you all with me on this? That's R of t. It's called a ramp function. What does this look like then? What does R of t minus 5 look like? Think about the definition. All right, for the impulse or the u of t function, we always looked at the point where what happened? The argument
Goes to
is 0, right? Where does that happen for this one?
R equals
T equals 5, right? So you go to 5. Now, after that, right, that's where the argument goes to 0. Here, the argument's 0 at 0, right? And then what happens, it just ramps up like this. That's it. That's all it is. Got me on that one? Now, the natural question is this. What is, I'm going to try to do this slowly. What does R of minus t look like? Think about that. Just think what we did with the u of t. What do you think happens? Well, if a ramp function looks like this, right, for t greater than 0, when is minus t greater than 0? When t is negative, isn't it, class? Mm-hmm. So it basically looks like this. Got me? That's the R of minus t. What do you think happens if I put R of 5 minus t? Where does it transition, class? 5 minus t is 0, t would be 5, correct, class? As a matter of fact, it's like drawing this, I call it drawing a slanted curtain this way, and now the whole thing, if I had R of 5 minus t, it would look like this. Slope is 1, 1 there, but it would look like that. Got me? And I might add, you can see that this might get a little tricky, right? And it does, in fact. But I have to make sure you see the basics. Once you see the way I'm thinking about it, I always want to know what the function looks like just with t, then with minus t, and then add some constant to it so you can see how it shifts to the left or to the right. Got me on that, class? And this is important you think that way. All right, next, after that, we're going to get a function that is used all the time. We're going to get 2 more functions. But, by the way, if I start running over, yell at me. I'm prone, I don't care if that clock's there or not. I'm prone to be in a habit of finishing the topic of discussion. But yell at me. Okay, just point. Because I look at the comments I got in my evaluations last semester. You never know what time it is. You go over 5 minutes continually. And frankly, they're right, yeah.
You said that was the R function is a ramp?
Ramp, R-A-M-P.
R-A-M-P. What was the name for the U function? Was there specific?
You can call it, they call it a unitary function, but frankly, I'm not even sure what our book calls it. It's u of t. It means it's a unit value of 1. And it's used to really, when we describe circuits, you're used to seeing a battery and a switch, right? Well, instead of that, they replace it with a voltage source with just u of t. And they'll put the magnitude of the voltage in front of that. That's what they use for a lot of stuff. All right, the next thing, and this is something I've got to be careful about. This is one you haven't seen, but it's so useful. This is called a pulse function. Pulse function. Or a rec function. Now, I want to be sure you understand this. It's simple, but difficult. And I say that for a reason. The pulse function is p tau of t. Tau is important, but that's the same thing as rect of t over tau. Now, the book uses RECT. Most journal articles, most things you see use this, pulse of tau, P of t. Now what it is this. It's something that has a height of 1 and a width of tau, which means this is at tau over 2, this is at minus tau over 2, And this is either the p tau of t or the rect of t over tau. You'll notice the important the important thing you have to catch about this is tau, because tau is the width, but it only has a height of 1. You all follow me? That's called a pulse or rect function. So the natural question I have is, what is either a pulse or a rect, say pulse of 5t, look like? Just tell me. This is t. Well, the width is 5, right? Well, pardon me. The first thing you got to do is say, where is it centered? When the argument is 0, correct? When is the argument 0? 0. Is it? Did you follow me on this? All right. The width is what? 5, right? Total width. So where does it stop at? 2.5. That'll bug people. Minus 2.5. All right. This is what it looks like. Still has a width of 5, but now it's stopping at in non-integer values. Follow me? Mm-hmm. And remember, you always have to find out where the argument is 0, the center. Now that would be the same thing as rect of t over 5. They're the same thing. It's always t slash the width on a rect function. That's all it is. So now the natural thing to ask is, what does something look like with a little bit of a modification? Let me just ask you this. What does p of 5 of minus t look like? Take a guess. It's the same. Whenever it's a minus t, just take this, flip it on its side. It looks the same. You got me on that, class? Which will become a very nice fact later on. You're going to see it's very useful. But what does this look like? Now what does p of, say, 6 of t minus 7 look like? I could put rect, but I'm just going to say, where do you always look at first? The center of the function is at what? 7, right? So find 7, put it there. The width is?
6.
Total width is 6, right? So you add 3, subtract 3, right? I add 3 to 7, I get 10. I subtract 3 from 7, I get 4, right? So it's this. Y'all with me? Mm-hmm. Now, this is something I assume people know, but I've learned not to assume certain things. If I put 5 on here, what changes? Goes up to 5. That's it. Goes up to 5. But if I don't cover that, somebody's going to say, well, we never covered that. I assume certain things, and it's dangerous at times. Because in fact, people that ask me that, state that, they're right. I didn't cover that particular thing, and I should have. It was scaling. Anytime you have any number in front of a function, it's just, I call it the weight. It's the magnitude the thing will go to. All right? Now 5 delta is still infinity, all right? But then the area goes to 5, not 1. Got me on that? Mm-hmm. The area under it, that's the difference. All right, I got through that. Finally, I'm surprised I got that far. We're gonna talk about a couple things that you know already. I know. Do you have, how many have a class after this one immediately? Oh, God. Is it in this building? Mm-hmm. No? No? Where's yours?
Parker.
Oh. How come they don't give you 15 minutes between classes?
Because they hate us.
Huh?
They hate us.
Really, how do you get from the vet school to in the engineering quadrant in 10 minutes? The people, some of these people have to go out to their clinics and stuff like this. I don't know how they do it. And I don't know who came up with this 15 minutes or 10 minutes between classes, because that's insane for people that have to go from here to, Parker you can get to in 10 minutes, I think, easily, but you can't get to certain other places. In the vet school are people that always are yelling about stuff. They have classes down here for anything. All right, I'll stop here. You know what energy and power is already, right? Power is V of t times I of t. Energy is the integral of power of t with respect to time. I'm going to give you some homework, and I'm going to send everybody a link. One last thing, I use OneNote. I don't use Canvas. The reason is I take the university out of everything I do if possible, because the university system, I've had problems with Canvas. Not last year I didn't use it, but in years prior would go down or something like this, and students couldn't see anything. And so I use OneNote. How many of you use OneNote? Good. I will send you a link. You'll get on there. Make sure you can see the homework and the syllabus and everything like that, okay? And frankly, if you have any questions, let me know. I'll send you your homework and I'll post the solutions in a bit. But I need to see.
We don't have lab, right, for this week?
Well, I don't know anything about your labs.
Cool, neat.
The reason is I was told, you don't have to worry about the labs. I'm like, great, I don't have to worry about them.
Nice, so.
But I didn't know, I don't know that. You know how you can find out really easy? You go up to the second floor, into the office, there's the, you know, those double doors, you go in there, and you simply ask Dr. Mark Nelms' administrative assistant, her name is Linda, and she will be able to tell you. I'll tell you what, if I find out, I'll send everybody an email, all right? Fair enough? But I don't think you have lab.
I don't think we do, but I'd rather have clarification than